Why does a shattered glass never leap back off the floor to reassemble in your hand? You are holding a glass of cold water on a quiet afternoon when your grip suddenly slips. It hits the hardwood and bursts into 100 glittering shards while water soaks into the grain. In that split second, you know exactly what has happened. You do not need a degree in physics to understand that those pieces will never spontaneously reform into a perfect cylinder. You have just witnessed the most fundamental rule of our reality. It is a principle so deeply embedded in your life that you likely never stop to question it. Time has a direction, moving from a past we remember to a future we can only imagine. Yet, the master equations of the cosmos suggest that the glass should be able to unshatter. The math does not care which way time flows. Whether you study Isaac Newton's laws of motion or Albert Einstein's theories of relativity, the equations work perfectly in reverse. If you filmed a planet orbiting a star and played the tape backward, the physics would remain valid. No forward or backward button exists within the fabric of space and time. There is only one exception: the second law of thermodynamics. This is the only law in all of science that distinguishes the past from the future. It states that in any closed system, a property called entropy, the level of disorder or messiness, must always increase. The shattered glass on your floor possesses much higher entropy than the glass in your hand. This single law is the reason why eggs don't uncrack. Wood doesn't unburn, and you are getting older every second. Rudolf Clausius first brought this concept to light in April 1865 at the University of Zurich. He realized that heat always flows from hot objects to cold ones and never the other way around. He coined the word entropy to describe this inevitable march toward disorder. It was a revolutionary idea because it suggested the universe has a built-in arrow of time. To put this in perspective, imagine a deck of cards. When you buy it, the cards are perfectly ordered by suit and number, representing low entropy. As soon as you shuffle them, you create disorder. The more you shuffle, the messier the deck becomes. Mathematically, there are millions of ways for a deck to be messy, but only one way for it to be perfectly ordered. The universe is constantly shuffling the deck and never puts the cards back in their original sequence. If the basic laws of atoms and particles are reversible, how does a one-way world emerge from them? In 1876, Joseph Loschmidt raised a massive objection to this idea. He pointed out that if you could somehow track every single atom in that shattered glass and perfectly reverse their speeds and directions, the glass would have to come back together. Logic dictates it should be possible. Yet it never happens. This created a paradox that nearly broke the minds of the world's greatest thinkers. If the small parts of the universe can go backward, why can't the big things? The world we see is fundamentally different from the world of the atoms that build it. Ludwig Boltzmann, a physicist at the University of Vienna, spent his life trying to solve this mystery in the late 1800s. He realized that the arrow of time is not an absolute rule, but a matter of overwhelming probability. Think about a box filled with blue gas on one side and red gas on the other. If you remove the divider, the colors will mix into a purple haze. They could technically unmix if every molecule happened to bounce in just the right direction at the exact same time. However, the odds of that happening are so small that you could wait for a trillion universes to live and die before you ever saw it. We see time move forward because the forward states are trillions of times more likely than the backward ones. This statistical reality means that our entire experience of life is based on a cosmic coincidence. In 1927, Arthur Stanley Eddington at the University of Cambridge officially named this phenomenon time's arrow. He argued that if you look at a system and see it becoming more disordered, you are looking at the future. If it looks more ordered, you are looking at the past. This arrow gives the universe its narrative. Without the second law of thermodynamics, nothing would ever truly happen because every event could be undone. There would be no cause and effect, no memory and no growth. We are only able to experience the present moment because the universe is constantly falling into a state of greater messiness. If the universe is constantly becoming more disordered, it must have started in a state of nearly perfect order. It's like finding a perfectly stacked house of cards in the middle of a hurricane. You know someone must have just set it up. Roger Penrose at the University of Oxford has argued that for our arrow of time to exist at all, the Big Bang must have been incredibly special. It had to start with an unnaturally low level of entropy. We don't know why the beginning of everything was so organized, but that initial order is the fuel that has been burning for 13.8 billion years. Every breath you take and every star that shines is just a tiny part of that original order slowly winding down. Some modern scientists believe that because time is based on probability, our entire sense of reality could be a statistical fluke. There is a terrifying mathematical concept called a Boltzmann brain. It suggests that it is actually more likely for a single, conscious brain to briefly flicker into existence out of the random chaos of space, complete with false memories of a past, than it is for an entire, ordered universe to evolve over billions of years. While this sounds like science fiction, it is a serious problem in the math of entropy. It forces us to ask if the history we remember is real or if we are just a momentary glitch in the rising tide of cosmic disorder. The arrow of time does not just explain why glasses break. It dictates the ultimate fate of everything we know. Because entropy must always increase, there will eventually come a time when the universe reaches its maximum messiness. Physicists call this the heat death of the universe. All the stars will burn out, all the black holes will evaporate, and the temperature will become uniform everywhere. When that happens, entropy can no longer increase. When entropy stops increasing, the arrow of time effectively vanishes. Without change, there is no time. The universe will become a static, eternal graveyard where nothing ever happens again. In the end, time is not a solid road we are traveling on. It is a one-way bridge built out of the sheer weight of probability. We live in a brief window of history where the universe is still transitioning from a state of perfect order to a state of total chaos. This transition is what allows us to see, to think, and to love. Every shattered glass and every fading memory is a reminder that we are part of a grand, irreversible journey. We are the witnesses to a cosmic clock that was wound up at the beginning of time and is slowly, inevitably ticking toward its final stop. We cannot turn back, and that is exactly what makes every passing second so incredibly rare. Why does the universe appear as a perfectly symmetrical playground when you shrink down to the size of a single atom? At this microscopic level, the distinction between the past and the future simply vanishes. Imagine a single planet orbiting a distant star in the deep silence of space. If you recorded a video of that planet's path and played it backward, even the world's most brilliant physicist could not identify the real version. The math works perfectly in both directions. Gravity pulls with the same strength and orbits follow the same elegant curves. Whether time flows toward next Tuesday or back toward last year. This is the great irony of our universe. The fundamental rules governing everything from the smallest pebble to the largest galaxy are time-symmetric, indifferent to the direction of the clock. In the mid-1800s, James Clerk Maxwell mapped out the laws of light and electromagnetism at King's College London. He found that his equations functioned like a two-way street. If you reverse the flow of an electric current, the physics remains consistent. A few decades later, Albert Einstein sat at his desk and revolutionized our understanding of gravity and time with general relativity. Yet, even his groundbreaking work treated time as just another dimension. Similar to height or width. You can move left or right, and you can move up or down. Mathematically, Einstein's universe allows you to move through time just as easily as you walk across a room. There is no forward built into the basic code of the cosmos. This creates a massive problem that has haunted science for over a century. If the building blocks of the universe are reversible, why is our daily life so stubbornly one way? We see mirrors shatter, but we never see the shards leap off the floor to reform into a perfect sheet of glass. We see smoke drift away from a campfire, but we never see that smoke pull itself back into a log. In 1876, Joseph Loschmidt stood up at the University of Vienna and challenged the leading theories of the day. He pointed out the reversibility paradox. He argued that if the microscopic laws of motion are reversible, then it should be impossible to derive a macroscopic law that only goes one way. He was asking how a billion two-way atoms could team up to create a one-way world. To understand why this is so strange, look at the way light behaves. When a beam of light bounces off a silver mirror, it follows a path that is perfectly mirrored in time. If you reverse the light particles, it would retrace their steps exactly. There is nothing in the laws of physics that forbids a ripple in a pond from traveling inward to toss a stone back into your hand. It sounds like science fiction, but the math says it is entirely legal. This symmetry is present in almost every major discovery in the history of science. From the way heat moves through a metal rod to the way planets tug on one another, the before and the after are mathematically identical. Ludwig Boltzmann was the man who tried to solve this mystery. Working at the University of Vienna in 1872, he developed a formula to explain why things seem to move toward disorder. He realized that while a single atom might be reversible, a trillion atoms are a different story. He used statistics to show that there are simply more ways for things to be messy than there are for things to be neat. If you have a box of white sand on the left and black sand on the right, shaking it will mix them into gray. The laws of physics allow the grains to unmix themselves, but the odds of that happening are so small that it would likely never occur in the entire lifespan of the universe. However, Boltzmann's explanation faced fierce pushback. In 1896, Ernst Zermelo, a mathematician at the University of Göttingen, used a complex proof to show that in a closed system, everything must eventually return to its original state. This meant that if you waited long enough, trillions upon trillions of years, the shattered glass actually would reform. This debate was a fight for the soul of physics. Boltzmann was so distressed by the rejection of his ideas and the ongoing disputes over the nature of atoms that he took his own life in 1906. Just years before his theories were finally proven correct by new experiments. What Boltzmann eventually gave us was a way to see the arrow of time not as a hard rule of gravity, but as a result of probability. He framed the second law of thermodynamics as an overwhelming likelihood rather than an absolute certainty. In his 1877 statistical formulation, he showed that the universe is constantly sliding from a state of high order to a state of high disorder, which he called entropy, but this answer only pushed the mystery back one step further. If the universe is constantly becoming more disordered, it must have started in a state of incredible, almost impossible order. Sir Arthur Stanley Eddington, a renowned astronomer at the University of Cambridge, was the one who finally gave this concept a name that stuck. During his 1927 lectures, he coined the phrase time's arrow. He argued that if you follow the trail of entropy, you are following the direction of time itself. He insisted that without this increase in disorder, there would be no way to distinguish the past from the future. Naming the arrow didn't explain where it came from. It was like finding a compass in the woods. It tells you which way is north, but it doesn't tell you who built the compass or why it's pointing that way in the first place. Sir Roger Penrose at the University of Oxford has taken this even further. Penrose argues that for our current timeline to exist, the Big Bang had to be perfectly tuned. He calculated the odds of the universe starting in such a low entropy, highly ordered state. The number he came up with is so large it's difficult to even write down. 1 followed by 10 to the power of 123. To put that in perspective, there aren't even that many atoms in the observable universe. It suggests that the reason time moves forward today is because of a specific, ultra-rare condition that existed at the very moment the universe began. This leaves us with a staggering realization. Every time you watch a sugar cube dissolve in a cup of coffee, you are witnessing a process that is only possible because of how the Big Bang started 14 billion years ago. The one-way bridge of your life, the fact that you can remember yesterday but not tomorrow, is tied to the birth of the cosmos itself. But if this arrow of time is dictated by the starting conditions of the universe, what happens when those conditions finally run out? If the march toward disorder is inevitable, does it mean that time itself has an expiration date? That leads us to a much darker question. What happens to the universe when the arrow finally reaches its target? Why does a shattered glass never pull itself back together from the floor? In April 1865, Rudolf Clausius stood before the Zurich Philosophical Society to present a discovery that defined this one-way street of reality. While studying the movement of heat through steam engines, the German physicist realized that energy does not merely move. It spreads out. He needed a term for this inevitable tendency for the universe to become cluttered and disorganized. So he chose the word entropy, derived from the Greek word for transformation. This became the second law of thermodynamics. Clausius proved that the entropy of the universe always tends toward a maximum. Things move from order to chaos, but they never return on their own. To understand this, we must look at the math of the mundane. Think about a deck of 52 playing cards. When you first open the box, the cards sit in perfect numerical order. There is only one way for those cards to be perfectly organized. But once you throw that deck into the air and let the cards scatter across the carpet, the possibilities explode. There are billions upon billions of ways for those cards to land in a messy, random pile if you pick them up blindly. The odds of them landing back in their original sequence are effectively zero. This isn't because a law of physics prevents the cards from being orderly. It is simply because there are so many more ways for a room, a deck of cards, or a galaxy to be messy than there are for them to be neat. Ludwig Boltzmann refined this statistical reality in 1877 at the University of Vienna. Boltzmann saw the world as a sea of rushing atoms. He realized that entropy is a hard calculation of probability rather than a vague idea about heat. He developed a famous equation, now carved onto his tombstone, relating entropy to the number of ways atoms can be arranged. Boltzmann proved that if you put a drop of blue ink into a glass of clear water, the molecules will eventually spread out until the water is a uniform light blue. There are trillions of ways for the ink to be spread out, but almost no ways for all those trillions of molecules to stay clumped in a single drop. The ink spreads because disorder is simply more likely. However, this realization created a massive problem for science that led to heated arguments in the halls of European universities. In 1876, Joseph Loschmidt pointed out a glaring contradiction known as the reversibility paradox. Loschmidt noted that if you look at the individual collisions of two atoms, the laws of physics work perfectly fine in reverse. If you filmed two billiard balls hitting each other and played the tape backward, it would look completely normal. Loschmidt asked why the big picture cares so much about the direction of time if the tiny pieces of the universe do not. Why does a broken egg never unbreak, even though every single atom involved in the crash is technically allowed to move in the opposite direction? The answer is both simple and terrifying. Scientists still cannot fully explain why the universe started in such an organized state. In 1927, Arthur Stanley Eddington at the University of Cambridge coined the phrase time's arrow to describe this one-way property of the world. He argued that if you find yourself in a world where things are getting more organized, you are looking at the past. If things are getting more cluttered, you are looking at the future. Entropy is the only thing in the known universe that provides a before and an after. Without it, time would be a flat circle where every event could happen in any order. We would be living in a world where a burnt log could spontaneously turn back into a fresh piece of wood. Think about the sugar cube you dropped into your coffee this morning. As the white cube hits the dark liquid, it begins to crumble and dissolve. The sugar molecules move from a highly organized, solid structure to a state of total dispersion. You can stir that coffee for 1,000 years, but those molecules will never gather back together to form a perfect white cube again. This is the second law of thermodynamics in action. Every time you see something break, rust or rot, you are witnessing the universe sliding down a hill toward total randomness. This law matters for your own life because it defines the limit of every machine and every living cell. In 1867, James Clerk Maxwell tried to find a loophole. He imagined a tiny, intelligent creature, later called Maxwell's demon, that could sit at a door between two rooms and sort fast-moving atoms from slow-moving ones. If the demon could do this, it could lower entropy and reverse the arrow of time. But later researchers, including those at IBM in the 20th century, proved that even the act of the demon remembering which atom was which would create more heat and disorder than it saved. Even information itself has a cost in entropy. There is no way to cheat the system. The sheer scale of this rule means that our entire existence is a brief struggle against the inevitable. Your body is a masterpiece of order. It takes energy from food to keep your cells organized and your heart beating. But even as you maintain your own internal order, you are releasing heat and waste, which increases the total disorder of the world around you. According to the leading theory of cosmology, we are only able to exist because the universe began in a state of extremely low entropy. Roger Penrose from the University of Oxford calculated that the odds of the universe starting this way by pure chance are 1 in 10 to the power of 10 to the power of 123. It is a number so large it cannot be written down. This brings us to a haunting realization about the history of our species. Every ancient ruin we discover, from the crumbling pillars of Rome to the buried cities of the Maya, is a victim of this same law. We build structures that are highly ordered, and the universe immediately begins trying to tear them down and spread their atoms back into the earth. Rust on a car, dust on a shelf, and the graying of hair are all the same process. We are living in a temporary window of time where the universe is still transitioning from that initial perfect order toward a final state of total chaos. We are the witnesses to a grand unfolding that can never be repeated. If entropy always increases, it raises a question that haunts every physicist who looks at the stars. If we know that the universe is becoming more disordered every second, what does the end of the story look like? Scientists have a name for this final state, and it represents the ultimate conclusion of Clausius's law. If the arrow of time keeps pointing forward, there must be a point where the universe runs out of order entirely. What happens to time when there is no more disorder left to create? To find that answer, we have to look away from the sugar cubes and the playing cards, and look instead at the very end of the universe itself. Why does your coffee cool down but never spontaneously heat back up? To find the answer, we have to look past the liquid in your mug and toward the very beginning of everything. Scientists realized that if the universe is a giant clock winding down, someone or something had to wind it up in the first place. This realization leads us to a mystery that makes the laws of physics look like a mathematical accident. For time to flow forward today, the universe had to start in a state of nearly perfect, impossible order. Think of a massive stadium filled with 1 million people, all perfectly silent, sitting in alphabetical order by their middle names. Physicists call this state of extreme organization low entropy. If the Big Bang had started as a chaotic, messy explosion, time as we know it simply wouldn't exist. There would be no past to remember and no future to predict. We would be stuck in a static, timeless fog where nothing ever changes because everything is already as messy as it can possibly be. Sir Roger Penrose, a Nobel Prize-winning physicist at the University of Oxford, decided to calculate just how lucky we are to have an arrow of time. He didn't just find that the odds were slim. He found a number so large that it defies human language. In his 1989 book, The Emperor's New Mind, Sir Roger Penrose revealed that the odds of our universe starting in such a low entropy, highly ordered state were 1 in 10 to the power of 10 to the 123rd. To put that in perspective, if you tried to write that number out by putting a 0 on every single atom in the observable universe, you would run out of atoms long before you finished the first fraction of the number. It is a level of precision that makes winning the lottery every day for 1 billion years look like a mathematical certainty. This staggering calculation created a massive problem for modern science. If the natural tendency of the universe is to slide into disorder, why did it start so incredibly organized? Cosmologists call this the past hypothesis. It suggests that the Big Bang wasn't just a hot, dense point, it was a moment of supreme, unnatural neatness. Imagine walking into a room and finding 1 trillion decks of cards all stacked in perfect suit and numerical order. You wouldn't assume it happened by chance. You would know that something very specific set them that way. This winding up of the cosmic clock is the only reason you can tell the difference between a video of a glass breaking and a video of a glass being filmed in reverse. We are living in the long, slow aftermath of a miracle of order. But here is where the floor drops out from under our understanding of reality. This reservoir of order is a finite resource. Every time you breathe, every time a star shines, and every time a heart beats, a little bit of that initial order from the Big Bang is used up forever. We are burning through the neatness of the universe like fuel in a tank. This means that the arrow of time isn't an eternal property of space. It is more like a fading echo. As the universe expands and matter spreads out, the difference between ordered and disordered starts to vanish. We are sliding toward a finish line where the very concept of later loses all meaning. If the second law of thermodynamics is an absolute ruler, it points toward a very specific and very bleak destination. Scientists call it the heat death of the universe. It isn't a fire or an explosion. It is the exact opposite. It is the moment when entropy finally wins and reaches its maximum possible value. At this point, every corner of the cosmos will be the exact same temperature. There will be no more energy to move, no more heat to flow, and no more stars to burn. Because there will be no more ways for the universe to get more disordered, the arrow of time will effectively vanish. Without a change in entropy, there is no way to distinguish 1 second from the next. The clock doesn't just stop. The concept of ticking becomes physically impossible. This brings us to a terrifying question that keeps physicists like Carroll up at night. If our universe required such a specific, low-entropy starting point, what happened before the Big Bang? Some theories suggest our universe is just one small bubble in a much larger multiverse where time flows in all sorts of directions. Others wonder if the Big Bang was actually a big bounce, and we are simply in the phase where things are getting messy before they eventually crunch back together. But the most unsettling possibility is that our ordered beginning was a total fluke. It might have been a momentary dip in the chaos that lasted just long enough for galaxies, planets, and people to form. To understand how strange this is, consider the Boltzmann brain paradox. In the late 19th century, Ludwig Boltzmann's critics pointed out something haunting. If the universe is just a game of random chance, it is statistically much more likely for a single human brain to spontaneously pop into existence out of the chaos, complete with false memories of a life, than it is for an entire, ordered universe to evolve over billions of years. It is easier for the universe to cheat and create the illusion of order than to actually be ordered. This forces us to ask, is the history of the world real? Or are we just a temporary flicker of logic in an ocean of nonsense? The more we study the arrow of time, the more we realize that our entire existence is a race against the inevitable. We live in the Goldilocks era of the cosmos. It is messy enough for things to happen, but ordered enough for those things to make sense. We are far enough from the Big Bang to have complex structures like DNA, but far enough from the heat death to still have energy to use. We are effectively surfing on a giant wave of crashing order. But eventually, that wave has to hit the shore. What happens to the laws of physics when the fuel of entropy finally runs dry? If every equation in science, from the way light travels to the way gravity pulls, works just as well backward as it does forward. Then the only thing giving our lives a sequence is this dwindling supply of cosmic neatness. When the last star blinks out and the last black hole evaporates into a thin mist of radiation, the universe will be perfectly symmetrical once again. In that darkness, there will be no difference between the past and the future. This realization changes the way we look at a simple sunset or a falling leaf. These aren't just everyday events. They are evidence of a cosmic beginning so precise it defies calculation. We are witnessing the slow, majestic decay of a perfect starting point. But this leads us to the final, most haunting mystery of all. If the universe is a clock that is slowly winding down toward a cold and silent end, what was the mechanism that wound it up in the first place? To find the answer, we have to look at the one place where time might actually stand still. Does the universe have a final horizon? We currently inhabit a cosmos that is loud. Bright and busy, stars burn. Hearts beat and your lungs pull in oxygen. Yet every one of these actions depends entirely on the slide from order to chaos. We are essentially living off the energy released by the cosmos as it falls apart. Eventually, this process reaches its natural conclusion. Scientists call this state the heat death of the universe. It is the moment when entropy finally wins. In this distant future, the temperature of everything becomes perfectly even. There is no more concentrated energy to move a piston, light a bulb, or fire a neuron. The universe becomes a vast, lukewarm soup where nothing ever happens again. When this state of maximum disorder is reached, the arrow of time simply vanishes. If you were to look at the universe during this era, yesterday would look exactly like tomorrow. Without the increase of entropy, there is no way to tell which direction time is moving. The cosmic clock does not just stop. Instead, the very concept of a before and after loses its meaning. We only feel the rush of time today because we are caught in the middle of a grand transition. We are the witnesses to a specific window of history where the universe is still organized enough to have a direction. You can see this law in action every time you look at your own life. Consider the objects you own. Your car requires constant maintenance to keep from rusting, and your home needs repairs to stop the roof from leaking. Even your bank account reflects this reality. Inflation is essentially the entropy of money. If you do nothing, the value of $1 decays over decades. To keep things in order, you have to constantly inject new energy and work into the system. This is why being organized feels like a struggle. You are literally fighting against the most fundamental law of the entire cosmos. Knowing this changes how you might look at a simple afternoon. When you see a sunset or watch the steam rise from a cup of tea, you are seeing the second law of thermodynamics in motion. You are watching the universe spend its limited supply of order. This makes the present moment much more than a fleeting thought. It is a rare physical state. In the multi-billion-year lifespan of the cosmos, this era of complexity and life is just a tiny, flickering spark. We are the lucky ones who get to exist while the arrow is still pointed forward. If you want to feel this connection to the deep future, look at the stars on a clear night. Every star you see is a concentrated pocket of low entropy, a small island of order in the dark. They are burning through their fuel, contributing to the inevitable rise of disorder. But that very process is what creates the light that travels across the void to hit your eyes. The destruction of that order is what allows you to see the beauty of the night sky. One day those lights will go out, and the sky will be truly black. But that day is not today. Arthur Stanley Eddington once said that if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. This law is the ultimate referee of reality. It dictates that you cannot unring a bell or unspill a glass of milk. It ensures that memories only go one way. It is the reason we have a history to remember and a future to plan for. Without this one specific rule, the universe would be a static, unchanging photograph. Because of it, the universe is a movie. How do you live with the knowledge that everything is slowly drifting toward chaos? You recognize that order is the most precious resource in existence. Every time you create something, or clean something or learn something, you are temporarily carving out a space of low entropy. You are using energy to push back against the tide. It is a battle you will eventually lose, but the fact that you can fight it at all is a miracle of physics. Your daily efforts to maintain your life are a direct conversation with the laws that govern the stars. The next time you drop a glass and watch it shatter, do not just see a mess. See a physical demonstration of the beginning of the universe. The shards on the floor are in a state of higher entropy than the glass in your hand. You have just witnessed the arrow of time in its purest form. You are seeing the same force that drove the Big Bang and will eventually lead to the quiet end of all things. It is a small, domestic version of the greatest story ever told. We are travelers on a one-way bridge. Behind us is the perfect order of the beginning, and ahead of us is the perfect chaos of the end. We exist in the sweet spot where the bridge is still standing. We have the light, the heat, and the time to wonder why it all works this way. The universe is a grand machine that is slowly winding down, and we are the brief, beautiful sparks generated by the friction of its gears. Imagine the last grain of sand falling through an hourglass that spans the life of everything. When that grain hits the bottom, the story is over, but for now, the sand is still falling. The arrow is still flying. The sun is still warm on your skin, and the future is still waiting to be written. The law of entropy makes life temporary, but it is also the only thing that makes life possible. Subscribe for new breakdown like this every day.